right, so let's see. For you guys, this should be page 120. This is Thermodynamics, April 19, lecture or class 22. All right, so one more thing left, material was speaking, but it's one line or two lines. So basically, we did the problems for the entropy change for closed system. So we have left what type of systems? So for open systems, or what is the other name for open systems? Control volume systems. What do we have? So what is the equation for, what was the equation for the, so for we say the total change of entropy was equal to what? Yeah, plus I think was environment, no, or surrounding. I think I put surrounding on the previous class notes, plus the delta S of the system. So what was something specific about the change of the entropy of the surrounding is that it was equal to what? Minus delta Q over T plus M S2 minus S1. So that was for closed system. What is the biggest difference between a closed system and an open system? Is that there is mass flowing, no? Okay, so really over here, what should we have? An M dot. So this Q is going to become what? Q dot. And that's all there is. Okay, I know I did it the last time, but can anyone remind me what is the origin of that negative sign? It's because from the Clausius inequality, what was the Clausius inequality? Is that if a system, if delta Q over T is equal to 0 is reversible, or what is the other one? If it was negative or equal than 0, no? So what happened? Oops. So I forgot the most important part here. This is the principle of increasing entropy, so this should be like this. So, after that little, well, no mistake, but I forgot to put it. What happened to this inequality if you reverse the order of the higher or equal sign? What happens when you reverse the sign? I think what happens when you reverse the direction of the symbol? You need to reverse, you need to put a minus sign, no? That's from where that minus is coming from. Okay, so really that's all. So let's do a problem that we're going to do it two different ways. So again, instead of picking completely randomly problems, I look at the problems of the homework and try to pick problems that were The one before, the one after, okay? Or close to each other. Yes?
Is that m dot the same as the one before? It was AB over
The mass flow over here?
Yeah.
Yes. Yes. So basically, we're going to be looking at problem 687. And we're going to solve it in two different ways, okay, for the understanding, so you have a good understanding of the material. So let me go to 687. All right, here it is. Oops. So 687, see if I can move down my page. All right, I think I might have to zoom out a little bit. All right, so problem 687. So air at 400 kilopascals, 970 Kelvin enters a turbine. So we do the sketch of a turbine. If you don't know the real symbol they do for a turbine, it really doesn't matter. What can you do? Just do a box and say turbine, okay? Not a big deal, okay? So, okay, so the turbine, what do we have? We have air. That is going in, obviously it's going to come out. We know the initial pressure is 400 kilopascals. The initial temperature is 970 Kelvin. Exits at 100 kilopascals and at 670 Kelvin. In the process, they say steady state. Okay, heat transfer from the turbine occurs at an average outer surface temperature of 315 Kelvin. So basically that means that the temperature of the surface of the turbine is 315 Kelvin. So heat transfer from the turbine. So what does that mean? That is leaving the turbine, no? At the rate of 30 kilojoules per kilogram. So 30 kilojoules per kilogram. So really, what is this? Of kilograms of air flowing. So really, it's not Q, but Q over M, no? Okay. So kinetic and potential energy effects are negligible. So what does that mean? Energy equal to 0. Determine the rate power in kilojoules per kilogram. Okay, so what do we need to solve here for? The amount of work in kilojoules per kilograms. And what else we need to find? The entropy production within the turbine. And we need to solve for delta S. Okay, so what is our system? The turbine, no? Is that important? Yes, because if you don't tell me the system, I'm going to say, where is that equation coming from, no? Okay? So first thing we need to do is solve for the amount of power created by the turbine. Okay? So we know this is steady state, so that means that the energy production was 0. So we can say applying first principle thermodynamics, but I'm not going to say to the system. So what is the first principle of thermodynamics for control volume? So it's Q, but instead of Q is Q dot plus power, work dot, plus, if we neglect kinetic and potential energy, what are you going to have? M dot times what? H1 equal M dot H2. Everybody understand that equation? At least you should, okay? Okay, so maybe something we can do is to divide by the mass flow right away, so we get will be equal to H2 minus H1. I did not finish reading the problem, okay? So we're going to go back. Yeah, we don't need the rest of the information, but okay, so sorry for that. This is very bad what I just did. Is that I went, so kinetic and potential energy effects can be neglected. What do they say next? For air as an ideal gas, Cp equals to 1.1 kilojoules kilogram Kelvin. So for ideal gas, so for air, ideal gas, so just write down over here Cp equal 1.1 kilojoules per kilogram Kelvin. What is that? Why is that important? Okay, let me go to the next page and work it out. So basically here what are we trying to solve for? First thing about the power, no? W over M. So we're going to get will be equal to what? H2 minus H1 minus Q dot M dot. Okay? So let's say this will be equation star. Okay, so what do you know about an ideal gas? What is something important to know about ideal gases? Is that they do not change state. So if a substance does not change states, what does that mean about the properties? They kind of remain more or less constant, no? So the change of entropy is proportional to what? Okay, Cm or Cp delta T, there is no mass, but you're right. Actually, you're right, it should be Cm, should put the m dot over there. But let's just say this should be equal to what? Cp T2 over T1, no? You can put the mass flow, but we're going to be dividing by the mass flow anyway, so. Yeah, I mean, is this something new or were you aware of this?
No,
We did it, no? But this is important, guys. Okay? So if we use this transformation, the equation above, so the equation above becomes what? So basically, we should be able to solve the problem by either using the star equation or the double star equation. Okay? So, what's going to happen is that if we use the star equation, we'll be using what in order to solve the problem? The tables, and here we can just do the numerical application, no? But, yes?
Can you explain where the mass goes, how it disappears from that thing when the delta H?
On this one?
Yeah, no, below that. So that, I think previously you had written your
This
delta
one?
H as CP, previously it was practiced that the delta H is CPM delta T. Where does the M go exactly? Why do you have that?
Okay, what happened is that it depends really what you need, okay? So, let's say the one I wrote over here is delta H equal to Cp delta T. What are the units? I mean, what does the lowercase means in thermodynamics?
It's a mass, or
It's per unit mass. So what happened is that if you had, so basically if you had the mass, it will be no per unit mass, it will be this. So then you will have, I know that notation can be a bit confusing, okay? Because all right, so okay, so let's say using star, we need to go to the table. So what are the tables for the air? It was like 820 or 22, no? So that's 355, 22. Maybe from here I can go one by one. 21, 22. So this is table 822. So write down on this one table A22. Okay, what do we know? So let's first look at the table, okay, and see what the table gives us instead of. So the table is, what does it give us? It gives us the temperature, no? Okay, so if we look at the problem, do we know the temperatures? So what is T1? T1 is 970, and T2 is 670. So let's see, 670 right here. So what is the value for H? So be careful because I'm doing the second one first. So 681.14. And 970. Okay, they don't give us 970, they give us 960 and 980. So what can we do? But I mean, the interpolation will be equal to what? To the average. So what about you do the average between 1055 and 1023.25? What would be the average? 1000? 11.9. Okay. All right. So now we can say what? So W over M equal to H2 minus H1 minus Q dot over M dot. This will be equal to what? 681.14 minus 1000.9 minus, and what is Q? Again, everything comes from the figures. Well, what is Q? But is it positive or negative? It's negative 30, no? It's coming out. Yeah, so here we have minus 30, no? Yeah? So what do you find if you do the calculation? Yeah. Minus 300.76.
Yep.
Okay, so what does that mean? Is the turbine doing work or receiving work? Receive or doing? Doing work. And that's a good thing, no? The turbine should be doing work, no? Alright, so now we're just going to do exactly the same thing but using the double star equation, which is what? Okay, in this problem, obviously, they were not asking you to do both of them, but I'm doing both so that you can fully understand it. So what is the value of Cp that they give you? 1.1, and then the temperatures were 670 minus 970 minus 30. So this gives you work over m. So this is 300 times 1.1 will be 330. So this will be minus 300. Yep. I mean, 300 times 1.1, 330, no? So there is not much difference. Any questions so far? Okay, so let us keep going. So the next thing we need to see is that what is the change in entropy? Okay? So I always need my figure, okay? I always need my figure. So 122. What would be the total change in entropy? We don't know m, okay? But it's not a big deal. So this is the equation, no? All right? So do we know delta Q? Didn't we just what is delta Q over here? Is negative 30, no? Yeah? Okay? What is T? What temperature should be T from the figure? Should be the TS, the 315. So we say this is TS here, TS equal 315. That's good. But again, we don't know we don't know the mass, so they ask us to find the change in entropy per unit mass. So what can we do? Yeah, will be equal to 1 over, how can I do this? TS over m dot plus S2 minus S1. Okay, so from where can we get the S2 and S1? We can probably get it from two different ways as before, but if we look at table 822, this is the one that I don't like to use. To tell the truth, I don't like it at all. What do they give us here? Do they give us S or do they give us S upper naught? S upper naught. Is S upper naught the same thing as S? No. So what was the difference? So again, we're going to derive it because you know I don't like cooking, just to take one equation. So this is a good review. So there we go. Once upon a time, what was the starting equation for us? Q plus, oops, remove the dot, no dot. What is the first principle of thermodynamics? Neglecting kinetic and potential energy. Heat plus work equal to what? Change in internal energy. So that is the first principle of thermodynamics. First principle of thermodynamics was deficient in trying to prove what? The direction of the processes, no? What is that equation that helps us to define the direction of the processes? So ds equal to what? dq, correct, or delta t over dq. So we get from this one that delta q, which actually is our q, will be equal to what? TDS. Do you remember we derive all those TDS relations, no? Which is basically what I'm doing again. So, if I do that, this equation over here becomes what? TDS plus work equal to change in internal energy. Okay? So, what is the work done by the pressure? Minus PdV. So that equation becomes actually what? TdS minus PdV equals du, or the first TdS relation was what? du plus PdV. So now you're like, what the heck are we doing all that stuff, no? Understanding, again. Remember, to me, it's not that much about the result, it's the understanding. So now, how do we relate this to the enthalpy instead of the internal energy? What is H? What is the definition of enthalpy? Is internal energy plus work done by the pressure. So, if we take the derivative of H, that will be equal to what? du plus PdV. Am I missing anything? What? Plus V dp is the full derivative, no? So now if I do this, I can rewrite du as what? Equal to dH minus PdV minus V dp. If I substitute over here, we get the second TdS relation, which is what? TdS equal to what? dH minus PdV minus VdP plus PdV. What happens over here? PdV cancels, so we ended up with the second TdS relation, TdS equal to dH minus VdP. So we just use it in this problem, in the first part. What is dH equal to? Cp dt, no? And now, if we use the ideal gas relation, because the air is an ideal gas, PV equal RT. What is V equal to? RT divided by P. This is like the fourth time that I do all this stuff, but again, it's important for the understanding. So that equation over here becomes what? TdS equals to Cp dt minus what? RT dP over P if I divide both sides by T, what do you get? ds will be equal to what? Cp dt minus R dP over P. So next, just going to rewrite the same equation. So ds equal to Cp dt over T minus R dP over P. So now, what happens if we integrate this expression? So the left hand side will become what? S2 minus S1. And now this is the part that is a little bit difficult. This one I will give you, okay? This is the only thing you need to kind of remember is that this is what is basically equal to the S upper naught. So this is equal to S upper naught T2 minus S upper naught T1 minus R of what? What is the integral of dP over P? P2 over P1. Okay. So let's say it will be our letter I. But I don't know why I mean, this is the way they actually solve the problem, the solution. But what happens if you assume CP constant, which in our problem is constant? You can put it outside the integral. So then this becomes what? S2 minus S1 equals to CP natural log T2 over T1, or let me put it here, minus R log P2 over P1. And that will be equation 2. Okay, guys, so you need to understand this derivation and know how to do it. Because, okay, what is something I don't want to see on the exam? You need to find the change of entropy, and suddenly, magically, you write down this equation. Are you showing me that you understand the material? No? Okay? What I'm interested is throughout all this process we went over here. This, whatever, 3/4 of a page, no? That's the part that I'm interested. That's where you show me the understanding. So again, we're going to solve it in both ways. So using the first one, from where do we get these values? From the table, no? What was the table? Table 822. And we had at T1 equal, what were the temperatures? 970 and 670. So we go to the table. $822, so let's do first 970 since we are here. So what do we do over here? You need to do the average. So what is the average of 2.92128 plus 2.94468? I don't know why they give that many decimals. But it's going to be 2.93 something. Again, if you don't practice in class, what's going to happen? You're going to miss the shot, no? Remember, like free shots, nothing complicated to understand. But if you don't practice using those tables and do those things. So what's the average?
3.93298.
Okay, now go to 670. What's for 270 the value of S? $2.52589. So 2.52589. Okay, in this equation, what is R? Is R bar divided by the molar mass, no? From the page you can use on the exam, what is R bar? And what is the molar mass of the air? 28.97. If you don't have that one, you get it from table A1. Okay, let me put it here. Table A1. Okay, so if you substitute what do you get? So 2.52589 minus 2.93298 minus 8.314 divided by 28.97 log. What is P2? I don't know, I don't remember. So P2 is 100, P1 is 400. P2 over P1, so it's 100 over 400?
Yes.
So it looks like you're going to get a negative sign. Should be a small value. You cannot get a positive. No way. And anything should be small because this is going to be small and this is going to be small. So what do you get?
Negative 0.00916.
Okay, so let's see if we can do everything on the same page. So using the second equation, which is what? S2 minus S1 equal to what? Cp log T2 over P1 minus R log P2 over P1 is equal to what? 1.1 log of 670 over 970 minus 8.314 divided by 28.97 log of 100 over 400. So I'm going to write it here. We're not going to get exactly the same, but I hope we get something close. So what do you get?
Negative 0.0000917.
Okay, so even closer than I was expecting. Okay, so again, you don't have to solve the problem both ways, but you have two ways to solve the problem, no? Okay, now my question is, what does it mean that the value is negative? Is that a big deal or no? I'm asking you this because what is that equation we had before? Yeah, maybe. Okay, so let me just rewrite the equation. Maybe I forgot to add something to that equation. 121, 122, 123. So 124, the total change in entropy is what? Okay, I'm just gonna redo the derivation again. Sorry for that, but I should have wrote the one before, but let's just rederive everything. And what do we know about these ratios? That it needs to be higher or equal than 0. Remember the principle of increasing entropy of the universe. So we just rewrote that equation as the total change of entropy per mass will be equal to minus 1 over T surface delta Q over M dot plus S2 minus S1 higher or equal than 0. So my question was the following. We know that S2 minus S1 is negative. So what needs to happen to this term in order for this process to be possible? It needs to be positive and high enough to make it higher than 0, no? Okay? And that comes from this delta Q. So over here, what do we have over here? So we had numerical application, the delta S over M dot is equal to what? Minus 1 over, what did we say was TS? What is that figure? What is TS? The temperature of the surface, so 315. The delta Q over M is equal to what? Negative 30. That's why this is going to become positive. Plus what we just calculated, so negative 0.0091, it doesn't matter, 17, okay? Let's use that one. So I hope you get something positive. So what do you get? What is it?
0.086.
Okay. So what does that mean? Is irreversible, no? Because you cannot reuse the energy, no? Even though it's pretty close to 0, but any question about this problem? Okay, so I went through every single detail in this problem, no? For the understanding, so. All right, let's see if we have time to do another one, but I will not go in that much detail. I might just give you the steps. Okay, next problem we're going to look at is 6,102. And this should be page 125. Okay, so let's do something. Since we only have 20 minutes, I'm going to do the problem like I will do it like I would like to see it in class, okay? I might not do all the substituting the values, but I'm going to go through it like I think you should do it. So 6,102. So I have less than 20 minutes, but that doesn't mean I'm going to rush. I'd rather not give values, but finish everything else. 6. All right, here it is. All right, so let's see. Okay, this is the part that I always spend most of the time, is reading the problem. So steam enters a turbine. So I will do the sketch over here. This is the symbol of a turbine. So I know it's steam enters a turbine at steady state. So P1 equal 6 megapascals. T1 equal to 600 degrees Celsius with a mass flow of 125 kilograms per minute. And exit as saturated vapor at P2 equal 20 kilopascals, producing power at a rate of 2 megawatts. Okay, so I know it's steady state. So kinetic and potential energy can be ignored. Determine the rate of heat transfer in kilowatts for a control volume. So we need to find, what do we need to find? Q, okay, I don't know if it's go in or out, okay, but Q. For the control volume, what is the system they want us to use? The turbine, so this is our system. So that's important to let me know what the system is, no? And then part B, the rate of entropy production for enlarged control volume that includes the pipe and enough of the surrounding that heat transfer occurs at the ambient temperature. So T outside here, T outside over here, T surrounding is what? 300 degree Kelvin. Okay. Okay, so over here might not be needed, but just in case, you know, I like figures, so I like to do a lot of figures. So basically, what is the first state of the substance? They tell us it's steam. So what does that mean? Superheated. And we know the pressure is, oops, this is 1. P1 equals 6 megapascals. And now, this is go to what state? Saturated, which will be over here. This will be the process, no? All right. Now, for the control volume, I can write down the first principle of thermodynamics. That will be what? Q dot plus work dot plus what? M dot H1 will be equal to what? M dot H2, no? Okay, what do we need to solve over here for? So Q dot will be equal to what? M dot H2 minus H1 minus the power. Okay? So over here, let's say I don't do the applications. So what is the value of the work? What's the value of the work? Will it be positive or negative? It will be negative because it's coming out, no? Yeah? Okay? What will be, so H1 will be equal to what? So, oops, I did here this is 2, sorry. So H1 will be equal to what? Probably from table A4. So let's see if I'm not going to do the substitution, but let's see if I can find the value. So what do we know about 1 is 6 megapascals and 600. So A5, A4, let's see, 6 megapascals. 4, 5, 6, 600, 3,658.4. Okay, what about H2? H2 is going to be equal to H gas, no? From the figure. So that one probably from the previous table, I'm guessing A3. Is that the one for the pressures? So 100, so what was the pressure on that one? How much? 200. So 200 what? Kilopascals? 20 kilopascals. So that will be how many bars? 0.2 bars? No? Yeah, I think that's correct. So what should be the H? Should be H sub H, no? So it will be table A3. $2,609.7. Okay, and here, because I got a little bit of experience, what should be the units of power? Should always be per unit second, no?
Yeah.
So what should I do with this? This should be 125, really do what? Okay, kilograms per minute times 1 minute equals 60 seconds, no? So it's going to be divided by 60. Okay, and here be careful because this is going to be 2 megawatts, so it's probably going to be 2,000 or minus 2,000 kilowatt, no? I'm guessing. So again, go and substitute the values, you find, I mean, we probably have plenty of time. Can you do a calculation for me? So it will be 125 divided by 60 times 2,609.7 minus 3,658.4 minus 2,000. I mean, I probably have the value with me, but I hope it's correct. 6102. If we didn't do anything wrong, they say it should be minus 184.8. What you got? Minus 184.8 kilowatts. Okay, I'm doing like if I was doing it. Now the total change in entropy should be equal to what? No, I just write down this equation. Okay, so what is in that equation? The delta Q over here. This delta Q here is equal to what? So delta Q over T will be equal to what? Minus 184.8 now divided by what temperature? The T of the surrounding, no? Which is 300. Now M is the same as before. From where do we find S2 and S1? Table again A3 and table A4, no? So you want to put it here. Table A4 should give us what? S1. Table A3 should give us S2. So let's see, this is for 2. What should be S? Should be equal to S gas, no? Yeah? Which is equal to what? 7.9085. And now from table S4 we know that is S1 is equal to 600 megapascal and 600 degrees Celsius, so A4, 6 megapascals, 6 megapascal at 600. What is the entropy? 7.1677. So whatever you want. So you see, I mean, it's not that I'm being perfect on the presentation. I will do like I will do it fast. But did I get everything done? And we got it done in what? In 15 minutes? So what is that value? 2.16, they have over here. Okay, guys, so you see, you can go, I mean, obviously, I got a lot of experience, so I'm not a good reference, but you see that it's not that this problem will take you like the first problem, like almost an hour? No, 50 minutes? And this one took us how much? 15 minutes, no? But it was about the same. What happens is that on the other one, we went very slow in order to show everything. All right, guys, so I hope you are doing the last two homeworks wisely, okay? Let me put it that way. Because so far on the exam, I haven't given you anything that you haven't seen before. So on this exam, probably I'm going to give you something that's going to come either from the homework or the class notes, no? All right, so work on those homeworks. All right, guys? And show me that you understand the material. Have a good afternoon and good weekend.